Hi, in this video we are going to talk about double replacement reactions. So as you may recall, a double replacement reaction has to have two ionic compounds reacting together to make two new compounds. So for example, you've got AX plus BY, and two sets of elements switch places. So A and B switch, and now A gets bonded to Y, and B gets bonded to X. All of these are ionic compounds. A and B are metals, X and Y are nonmetals. The ionic compounds that you start with as reactants have to be in the aqueous phase. When ionic compounds are solids, it's very hard for them to react. But if you dissolve them in water, the ions are free to move around and hit each other and rearrange themselves more easily. So let's pretend that you have a beaker filled with water with these particular reactants. And let's just say that they're all either +1 or -1. So since they're all ionic in this beaker of water, they're going to be floating around in the water like that. Now let's say that your products are also both aqueous. Now in your beaker, your products are A plus bonded to Y minus, but it's in water, so the ions are actually separated from each other. And then you've got B plus and X minus, also floating around in the water, not bonded to each other. So if you look here between the reactants and the products, nothing changed. Nothing changed. This means that this reaction does not happen. You're always going to have to start with two aqueous ionic compounds as the reactants, but if you get two aqueous products, this reaction actually does not occur. Something new has to be made. Well, let's say that BX was not aqueous. So we're going to get rid of those ions for BX. Let's say BX was actually a solid. Well, that means that it wouldn't broke up into ions when it's dissolved in water, and it would just settle at the bottom of the beaker. This is the key and the most common type of double replacement reactions. It's forming a precipitate. You put two aqueous solutions together. You got one aqueous compound, but all of a sudden a precipitate formed. Something clearly changed between the reactants beaker and the products beaker. You have this new substance. So you might be asking, how can I tell what's soluble and what's not? What is aqueous and what is a precipitate? Because that's going to be important to tell me if the double replacement reaction actually occurs. You're going to use solubility rules, and this is the table that we are going to use, and you must memorize this. And it definitely has some patterns to it, but this is a table that you're going to have to memorize. Anything that is soluble, meaning soluble in water, that's what we're talking about here, has the phase AQ, aqueous. The exceptions to that are on this side. The exceptions mean that they're insoluble, they're solids, therefore they are precipitates. Now, same thing down here, but the opposite. Insoluble, any compound that has these anions here, that's not part of these exceptions, but that if these anions are going to be solids when they're put in water. The exceptions on this side are going to be aqueous. Let's do an example. If you have ammonium carbonate and calcium chloride reacting together. Double replacement reactions, two ionic compounds. They both should be aqueous, they both should be soluble, but may as well just practice using our table here. We know that this is soluble because carbonates are down here, but ammonium is one of the exceptions. So this is aqueous. And calcium chloride, here are the chlorides. Calcium's not among the exceptions, and up here you've got soluble things. So this is also soluble, this is aqueous. Now to figure out the products, what I often do is think about a double replacement reaction as having four pieces, A, X, B, and Y, each of the ions. So there's your cation and your anion for that particular compound. Here's your cation and your anion for the second reactant. The insides and the outsides, quote unquote, are going to come together. So the metal and the nonmetal from different compounds and the metal and the nonmetal from different compounds will come together. So the ones on the outsides and the ones on the insides. You just have to remember one thing. You have to remember to flip the ones on the insides. Let me show you what I mean. When I rewrite this, when I combine ammonium and chloride, I'm going to get ammonium chloride written thusly. And my second product is going to be calcium carbonate. So you do not write the carbonate before the calcium. It's always, metal is always first in a formula. Well, let's make sure this double replacement reaction actually occurs. We should have one of the products be a precipitate, insoluble, solid. Well, let's look at this one first. We've got ammonium chloride. Here are the chlorides. And only compounds of silver, mercury, and lead 2 are insoluble with chloride. All the rest are soluble. So ammonium chloride is soluble. It's aqueous. Let's look at calcium carbonate. Here are the carbonates. Carbonates are all insoluble except for ammonium and alkali metals. Well, calcium is an alkaline earth metal. So calcium carbonate is insoluble. It is our solid. It is our precipitate. It is our proof that this double replacement reaction occurs. Now that we know this reaction is good, we can quickly balance it, and the only thing we actually need is a 2 there to balance the ammoniums and the chlorides. Let's look at one more example. Let's say you have sodium iodide and barium sulfide. We know it's double replacement because we've got 2 compounds, and I assume they're aqueous, but let's double check. Sodium iodide, here are the iodides. Sodium is not among the exceptions, so this is soluble, meaning the phase is AQ, aqueous. Barium sulfide, here's sulfide. Barium is among the exceptions in the insoluble section of the table. So barium sulfide is aqueous. Now to figure out our products, again, this is my advice, thinking about it in 4 pieces. Those 2 ions and these 2 ions. And combining the outsides and the insides. So we've got sodium coming together with sulfide. Well, one of these products has to be solid, has to be insoluble for this reaction to actually happen. So let's see if it happens to be sodium sulfide. Well, find the sulfide here. And sulfides are usually insoluble, but is sodium among the exceptions? And it is, because sodium's an alkali metal. So this one here, this product here, is actually aqueous. Now what about the one in the middle? What about the barium and the iodide coming together? Here's iodide. Iodide, most iodides are soluble. But let's see, maybe barium's among the exceptions. Oh, it's not. So this is also aqueous. You got two aqueous products. Therefore, just like our pictures of our beakers that we had previously, the reactants beaker dissolved in water looks exactly the same as the products. So this is actually no reaction, and you do not write any products. This double replacement reaction does not occur. The second type of double replacement reaction that you can have doesn't involve the solubility rules. It doesn't even involve precipitates at all. It is called an acid-base reaction or a neutralization. And obviously from the name, you're going to be reacting an acid and a base and neutralizing it. So this is just a type of double replacement reaction. So you have the precipitate type, and now you have an acid and a base type. So for example, let's say our acid is HCl, and our base is NaOH. Both of these are aqueous. Acids are always aqueous, and there are very few hydroxides that are not aqueous. So this is the base and this is the acid. Both are aqueous. Now, if you look at these in pieces, as we did before, ion pieces, you've got H plus and Cl minus. You've got NH, Na plus and OH minus. And you're going to use the same method. You're going to put together the outsides and the insides. So your products for this particular reaction are HOH, when you crisscross those, and NaCl. Remember to write the metal first. Wait a second. HOH, that's water. We have formed water and sodium chloride, which is a type of salt. Well, I know the phase for each of these. H2O is a liquid, and sodium chloride, if you're a little unsure of the phase of it, you can go back to your solubility rules. But anything that has sodium or any alkali metal as a cation is aqueous. So instead of a precipitate that we made here, the thing that's different that makes this equation happen is the fact that we formed water. Water is not aqueous. It is just a molecular compound, and it makes the products different than the reactants were. Let's look at just one more neutralization reaction. Here's an acid, sulfuric acid. All acids are aqueous. Here is a base, because it has an OH in it, ammonium hydroxide. If you need to figure out that that is aqueous, you can look back at the solubility rules. And let's just figure out the products. Again, I would write out the pieces, quote unquote, so I don't forget what the charge is for everything. And I'm going to put together the outsides and the insides. So my products for this particular reaction are HOH, which I know is H2O, and I always write the cation first, and then the anion, and when I crisscross those, I get a 2 around the ammonium. So this neutralization reaction did form water, which is something that's not aqueous. And if you want to prove to yourself that this other product is aqueous, the salt that you made, you can just, you're going to know your solubility rules, so you'll be able to figure that out easily. This is not balanced. The ammonium needs 2. The sulfates are good, but you're going to need twice as much water. If you go back and count your hydrogens and your oxygens, that's what you end up having for the balanced reaction. So here are just 2 examples to look at to illustrate double replacement reactions. The top one in blue formed a precipitate from 2 aqueous ionic compounds, and the second one down here was between an acid and a base, and it formed water. And these are the types of double replacement reactions.